So our next speaker will be Rick Koopman from Lenovo. Rick is the Director of HPC and AI Business in EMEA for Lenovo. He has spent a lot of time working with Lenovo and before that with IBM. And Rick will talk to us today about the path to zero emissions. Rick.
Okay. So everybody can hear me? Yes, I assume. So this is just to start with a good picture. This was our booth at Supercomputing 2 weeks ago. This is where we have been showing the history that we're having already with direct water cooling, starting in 2012. You just see a little bit of it with warm water cooling of up to 35 degrees Celsius, then 40 degrees Celsius, then at LRZ, up to the current generation that we're releasing now based on Sapphire Rapids with Ponte Vecchio, AMD Genoa, and the combination AMD Genoa H100 NVIDIA. So all on the wall. In the middle, you see one of the chassis that we install in the racks when we deliver those supercomputers. Again, standard 19-inch racks, 6-use chassis, and those building blocks that you see in there can slide into a chassis under pressure. So we can remove it, maintain it, slide it in under pressure. This one was running an HPL benchmark on Genoa. Anybody that's interested in the results can touch base with me afterwards. But we were pretty surprised with the HPL performance that came out of that because it was higher than AMD anticipated. So let's go on. HPC workloads. One of the end results of all the stuff that we're all doing with HPC, with our workloads, results in something that's centralized in the middle, climate change. Climate change that is highly influenced by the energy that we're using, even the energy we're using to calculate what the climate change consequences are. So if we want to influence what we're doing with climate change, we need to first determine where we stand, and we need to first determine how we can move from where we stand now to where we need to be. Now, I'm not going to talk about our products. I'm not going to talk about our solutions. We are in the top 500. We basically have 160 systems in the top 500. Number 2 and number 3 together in the top 500 don't come to 160 systems. So we have credibility. We're doing this energy friendly way of supercomputing already for 10 years. So I'm not going to talk about our products and how good we are in HPC. We're good, and we have a track record in doing that from HPC already to Lenovo. Now, in order to get to that picture on what climate change and influence all the consequences that we're generating with all the workloads that we're running, we need to first determine the base criteria that we're looking at, the base information that we're looking at. And what I've seen in the 25, 30 years I'm working in HPC is that too often we run into a problem where the guys running and managing the data center, being responsible for the data center, don't have anything to do with the guys running the supercomputers. That's something that is a big, big problem because those two together determine your total cost of ownership and the total cost of your operation. So if you don't know what the two together aggregate to, you have a big problem because then you're only talking about acquisition and you have no clue of what the operational side is going to mean for you. So that is something that we definitely need to bring into the picture. Now, kilowatt hour cost is one of the things that with a lot of academic institutions globally, the energy bill is not even seen by the guys that are running the supercomputers. If a kilowatt hour costs about $10 cents, that translates already to a very big budget. So 1 kilowatt hour is about almost $900 per year, 1 kilowatt hour, and that's for 10 cents. We're delivering racks now between 80 and 120 kilowatt hours. So do the math to determine where you stand now, where you need to be. Now, I also added the numbers for Europe in there, in the first line item, about 50 cents per kilowatt hour. So that's 5 times the cost of what you see for the 10 cents in the US. In Europe, the consequences with all the cost increases are huge on the energy side and have a big impact. In addition to that, you need to take into account that when you're running a data center, it's not only the bloody energy that you're using for your supercomputer, for your storage, and for your networking. Your cooling infrastructure adds about 40% of your cost, of your energy bill. Adds 40% to your energy bill that you would be paying for running your supercomputer environment. 40%. What else is important? This topic is, where is it? Pointer. This is very important in the US. We don't see it a lot in Europe. Usage of fresh water. That's the Googles of this world that are doing that in the middle of the desert, where they have used data centers, and when they're spoiling a lot of fresh drinking water. We're not doing that. Another topic that we need to take into account while determining where you stand is, what does a kilowatt hour translate to in the generation of CO2? It's about 0.44 kilogram. So every kilowatt hour translates to 0.44 kilogram of, say, CO2. So if you look at this basic picture already, you see that reducing power and optimizing your power consumption is going to bring you a lot of benefit and has a lot of consequences overall. This one should not be underestimated also. I'm going to give you a slide based on current and technology that's coming out now, what the fan consequences would be when you're running with air cooling on. Now, power generation. That's the base link to everything that's related to CO2 output. About 70% of all CO2 emissions is based on energy consumption. 70%. A third of that comes from the production of electricity. Now, fuel sources to create electricity. There's a couple of them, traditional ones. We have coal, still very, very often used. I don't know what the state is in South Africa, but in Europe, there's a couple of countries that are using a lot of coal. In Germany, they're demolishing complete historical villages to dig out brown coal and burn it 10 kilometers down in an energy plant. Not very efficient. Oil, also highly used. Gas, natural gas, 0.91 pounds per kilowatt hour is the efficiency. So you see oil and coal are not as efficient as gas, but they all come at a cost. Now then we have the no emission resources. Solar, hydro, wind. I don't know, again, what the situation is exactly in South Africa, but if I look at Europe, we have all of them. If I look at Scandinavia, there's a lot of hydro power in there. If I look at Switzerland, a lot of hydropower there. If I look at Denmark, mainly wind power. If I look at Germany and the Netherlands, a combination of wind power and solar power. The only country, by the way, in Europe that if the gas to Europe would be completely cut off and would not be any gas imports into the country would be Denmark. They have full coverage now by no emission resources in combination of wind and solar to cover everything they need from an energy perspective to satisfy their requirements. Now, I also put two in here that are debatable. Sustainable wood, what does that mean? It's wood and you burn it. For me, it translates like some similar to burning coal. A lot of people like it. Still, it burns a lot of stuff, and it has a big CO2 emission. Nuclear, it is emission-free. So now the European government sees that and realizes again that nuclear energy is emission-free, and everybody looks at emission and the reduction of emission. They're all planning building nuclear plants again. Typically at the borders of the countries, so that the countries don't only have them, but also the neighbors have an issue with the nuclear plants, because that's typically how they build the plants or where they plan the plants. Now, if you look at this picture, generation by source, about 40% is created by natural gas, 19% with coal, 20% nuclear, which is a serious percentage, knowing that a big number of the nuclear plants in Europe have been shut down over the last 10 years. They're rebuilding them now again. Renewables, about 20% coming in. Now, in a journey to emissions, to zero emission computing, there's a couple of phases that you're going through. This is the phase we're in now, or we're mostly in now, which is carbon positive. More CO2 released than removed. Most data centers are there, and most data centers are there typically because they have been built and constructed 10 to 15 years ago. And that's the legacy that we have with the data centers that we need to address now if we want to have our data centers play a better role in energy efficiency. Second step is, can we do this? Okay, carbon neutral, carbon release, CO2 removed. Yeah, we can reduce it dramatically using existing technologies. We've proven that already with most of our direct water-cooled supercomputer implementations and smart stuff that we add to it. Use savings from efficiency gains to justify the move to green power. Now, the third one is the end game. Carbon negative. The end game can only be delivered if this is completely in place and if we have moved away from this situation. So that means that you need to do smart stuff with the heat that you moved away from your IT technology. And the most efficient way to do that is through water, simply because the efficiency of heat transfer to water is about 4,000 times more efficient than heat transfer to air. So looking at that from a data center perspective, if you look now at the processors that are coming out with 360 and 400 watts, and how do you think you will be able to cool that with air? No way. So you need an Arctic hurricane in your data center, not an option. So direct water cooling is the only efficient way of transferring heat to away from the infrastructure. Now, attacking the problem step by step. Baseline is understanding the cost and understanding the source to determine the CO2. That's step one. So we know what we have in the data center. We know the energy that we use, so we know what the CO2 output is. Reduce it, so decrease consumption, be smart with the consumption by decreasing it and calculate the savings to justify a switch to green power and a push for green power. Now, innovation, recycle heat to do the CO2 offset. Now, I mentioned a couple of these things already. Now, CPUs are going up to 400 watts. That's what we're seeing. GPUs are going to 600 watts now. Memory per node, per two-socket node is 288 watts. Network adapters are consuming 50 watts. That aggregates to a lot of energy in a two-socket node format. Imagine a 1U tray with two sockets in there. You're over 2 kilowatts on a 1U tray now already. Now, what we also see is that if we look at future, and the future in the form of 2025, simple 42U 19-inch racks are going to need power connectivity of between 150 and 180 kilowatt. That is by 2025. So that's not in 10 years' time. That is the generation technology after the generation that is being released now as we speak. And there we already have 80 kilowatt racks and 120 kilowatt 19-inch 42U racks, which is already a big problem for most of the data centers that we're working in. Another issue that is causing a lot of issues is the T-case temperatures that are reducing. So due to the density, a increase of processor and GPU, the T-case temperature is getting lower. So where it used to be about 82 degrees Celsius, it's going down to 65 in the next generation. And that is going to cause for air cooling an even bigger issue than we see already now. Now, fans, I mentioned fans, not to underestimate the impact of fans. So imagine seeing this picture and then imagine running a direct water-cooled environment with no fans, where even your PSUs are direct water-cooled with a efficiency, heat transfer efficiency of 98% now. So 98% of the heat that's generated by your IT equipment is transferred to water. That leaves 2% that's not transferred to water, and that's called radiation. Because if you're cooling with water of 50 degrees Celsius, the metal that's in the infrastructure gets warm and radiates. So that 2% we're addressing with through other means than the direct water cooling, because that 50 degrees Celsius is the direct water cooling that we're using to cool the infrastructure. Now, fans again for air cooling, typical two socket server. 2022, now 900 watts. If you're going to 2024, 2025, fans will be using about 1,000 watts if we go on like this with a normal utilization. Now, think of the following. Look at where the 33% goes. It's there. So 33% energy overhead over the 1,000 watts if you would be really utilizing the computational power of your processor and really using it. So that's an overhead, an energy overhead of 33% caused by your bloody fans. Those little things that you have in your notes that you can click out in and out. They're causing a 33% overhead in your infrastructure. Now, let's translate that into numbers. 700 watt, 1U server. Computing value is about 640 watts. The fans will be consuming about 64 watts, about 10% of that platform. Now, taking into account again, 10 cents per kilowatt hour or 50 euro cents per kilowatt hour. This is what a typical 23 kilowatt rack, which due to the fans requires 25.2 kilowatt from a connectivity perspective and power consumption perspective. Look at what it means from a financial perspective in the right column. That translates to, in the US, 22K, which is more reasonable than the 100K. That is going to be what it is in Europe now with the 50 cents per kilowatt hour in Europe, in some of the countries. Germany is extreme at the moment. But you see the overhead that the fans only create on the infrastructure. Now add to that this picture, your data center, air cooling. What is air cooling? It's chillers, it's cracks that are pumping around cold air under the floor, holes in the ground, comes up, is pulled through your racks and up through the ceiling, returned again. This adds 40% to your energy cost. 40% to your energy cost. So this is not a smart and economic way of cooling your data centers, is it? Certainly, if you know that a direct water cooled infrastructure transfers that heat with an efficiency of 98% to water instead of into the air. So this is what we have now in our data center, guys. And one of the things I very often run into when I'm talking to a customer about direct water cooling is that they say, yeah, but we have an old data center and we only have air cooling and we don't have water in the data center. My first question then is, do you have chillers? Do you have chilled air? And the answer is yes. Okay, so you have water in your data center. Because that air is being cooled by chilling water. We need two connections to have a simple direct water cooled solution deployed for a supercomputer in a data center like this. Nothing more. Okay, now it went too fast. Yeah. Full impact of it. So the financial side we covered already. That is this now CO2. 1 kilowatt hour per year translates to over 4 tons of CO2 per year. That's only 1 kilowatt hour. Remember, racks going up to 120 kilowatt hour, spinning 24 hours a day. What does that translate to? Power. CO2 power 30K for the rack I just listed to you. CO2 141 tons. About 1/3 of it is overhead. The rest only delivers actual computing power. So fan power cost is about $1,900. Cooling power is about almost 9K. Total, no direct computing value on that simple one rack is 10K. And remember, in Europe, that's going to be about 60K euros. CO2 from the fans, from those bloody fans that you have in the notes, about 9 tons. So only by making the switch from air cooling to water cooling, you would already do this, reduce this and this. That's 49 tons reduction. Now, I have a problem visualizing 49 tons of CO2. CO2 is, I can touch it, I can see it, I can feel it. What does it translate to? Simple. To almost 2 elephants. That's what that translates to. Plus, that's for the fans, and for the data center, 8 elephants of CO2. Now, what does it translate to if you look at it from the things we're driving on a daily basis? That's what it translates to. Cars, each of these cars driving 110,000 miles. That's what it translates to, the stuff we're doing with one simple rack. That's what we can reduce to almost zero by making the switch to direct water cooling. Now, a couple of things. The question you asked on being smart. This is a solution, energy aware runtime. It's a solution we developed with Barcelona Supercomputing, and which is being deployed now at Barcelona, which is being deployed now at LRZ, it's being deployed now at SURF, also on AMD. So it's been enabled on AMD also. What AIR basically does on a runtime level is analyze the MPI communication, the outer loop of the MPI communication, determines, based on that, what the type of workload is, and dynamically reduces the frequency of the processors to still have the same runtime on the job. Or you can also define the parameters for same energy envelope.
Time for your last slide here. Thank you. Thank you, Rick. I think we have time for a couple of quick questions. Jeremy.
Of course.
Thanks very much. And to answer your question, it's an 80% usage of coal in South Africa at this point. Renewables are around 6.5%. So it's very low, but
a long way to go.
There's a long way to go. Yeah. The question I wanted to ask was just going back to this mismatch between the lead times on the facility and the IT equipment. We're sitting with that problem right now.
Oh, yeah.
Designing a data center for something we don't know what's going to go in there. Trying to define the interfaces between the two. What are they going to look like even in 3 years' time with this rapid change and struggling right now actually on the down select of the trade-offs for the cooling systems. Mm-hmm. One particular area that we're interested in is high ingress and egress. Water temperatures 45 plus and egress at 80 plus. Trying to recapture the energy from that system and match that to the IT equipment. What's the sort of general feel from your perspective on that?
Start with the data centers. One of the issues we're all struggling with is with organizations that design and develop our data centers that have a long track record in building data centers and have a long time experience in building data centers. That's what they've been doing for 40, 50 years. And they're using that experience to build those data centers based on that experience. Not looking forward and trying to adopt new capabilities and enable new capabilities. So that's one of the big issues. That's one of the big issues I'm struggling with every conversation I have with the customer. They truly are in the middle because they have the traditional data center guys that say one thing, and we, like I've shown you, are telling them already for 10 years that we need to change and we need to adopt and we need to change what we're doing in the data center and how we're doing it in the data center. So the first deployment that was on that first picture, that was a very big German supercomputer implementation, direct water cooled, 40 degrees Celsius. And one of the things that we had to take into account was the main goal for that deployment was energy reduction. So the reduction of energy consumption. We basically had to specify, based on technology that didn't exist yet, what the energy consumption was going to be. And it was part of a European tender. Now, European tenders can be pretty strict. So if you don't make your numbers, you're going to have a problem. So one of the things in the tender was that they basically said, this is the maximum energy consumption. And if you go above it, you're going to have to pay. We said, okay, that's fine. We're going to pay if we go over it. But if we stay under it, you're going to pay us. They've been paying us for 5 years. So we know what we're doing on a data center level. And I'm afraid that most of the companies, the traditional data center organizations, do not know where they have to be in a couple of years' time, even though we've been doing this already for 10 years. So what we do see happening is that the data center, the general data center management software that manages the fire extinguishers and the overall temperature and the interfaces with the cracks and the chillers, they're opening up. So what we're looking at is hooking up with their open defined APIs to interface and interact with that, so you can have dynamically also tweak the activity that a chiller has to execute on based on the temperature in the data center that is still there. If you're using chillers, if you're using water, it's a completely different story, because then you control it, because it's your CDU, your cooling distribution unit that you're managing. But still the 2% of heat that dissipates into the data center, you have to manage in one way or another. One of the things we're doing at LRZ, for instance, is that we have we use the 60 to 62 degrees Celsius water that comes out at the end of the loop, goes in at 50, comes out at 62 degrees. We're using that to create cold water through dispersion chilling. Efficiency now is about 60%. So that basically means that you have that you have free water, free chilled water. No energy consumption is needed to create cold water. You saw the 40% overhead that you need to create cold water and cool your data center. So that's free water. And they're using that to cool those racks that have network switches and storage devices in there and cover that 2%.
Thank you.
And does it answer your question? Okay.
Any further questions? Yeah.
Yeah, so the energy question again about profiling of applications and how they use energy. So once you've profiled an application, you understand which applications use how much energy.
Yeah.
Now that you have that information, have you ever considered feeding that into a scheduler so that in future you schedule for a certain balance of energy?
That's how we started. So we started about 6 years ago with energy aware scheduling. So basically collecting the profile of based from the job logs, collecting that job profile information, storing it in a relational database. The scheduler looking in the database based on the profile that he found in the database, define a profile of the IT equipment that is needed, and then change the frequency of the processors. So, but that was a static approach. So now we changed to the dynamic approach, which is energy aware runtime, which we developed together with Barcelona Supercomputing. And there's a spin-off of BSC now created based on the solution. It's called EAS, Energy Aware Services, based in Spain. Our previous distinguished engineer Luigi Brochard also works in that company, and we're working with them now in ever improving it on a dynamic approach. So profiling at runtime what the application behavior is by having 1 or 2 iterations of the outside MPI loop, recognizing that and taking action based on that.
Okay. Thank you, Rick, for that.
You're welcome.
A token of our appreciation.
Thank you very much.